As we think about phases and states of matter, it's important for us to take a moment to focus in on gases, because gases can be a really interesting way for us to explore matter and its interactions. To begin with, why are gases easy? In many ways, gases are really easy to study, but one of the really helpful things is that in a sample of gas, typically the kinetic energy of the particles is so much larger than the intermolecular forces that you can kind of ignore those intermolecular forces. Once we can ignore intermolecular forces, well, now the identity of the molecules doesn't matter. So it turns out that gases tend to behave pretty well because it doesn't matter what gas we're working with. For a lot of properties, the identity of the molecules doesn't matter. All that matters is how many molecules there are. Now, we have to be a little careful here. Sometimes people say, well, gases have no intermolecular forces. And that's not really true. And a water molecule has some dipole character. We can't just turn that off when it becomes a gas. What happens is the space between the molecules and the kinetic energy of the molecules is so large that we can often neglect, we can often just sort of ignore any intermolecular forces. But those intermolecular forces, the qualities, the properties of the molecules themselves still exist, and still exist exactly the same way as they do in a solid or a gas, or in a solid or a liquid. To help us understand gases, let's take a look at kinetic molecular theory of gases. So first of all, let's break that down a little bit. Kinetic, well, that sounds like we're going to talk about energy. Molecular, well, we might talk a little bit about how the molecules behave. Theory of gases. So kinetic molecular theory, KMT, provides a simple model that we can use to explain properties and characteristics of gases. So 4 main points in kinetic molecular theory. Depending where you look, sometimes these are broken down in different ways. But number 1, gas particles are much smaller than the space between them. So gases are diffuse matter, right? The matter that makes them up, the atoms, ions, molecules that make them up, are extremely far apart. Number 2, gas particles are constantly moving and experience elastic collisions with other particles and walls. So constantly moving, well, that sounds like they've got some pretty good kinetic energy, and experience elastic collisions with other particles and walls. What's an elastic collision? An elastic collision is one where we don't lose any kinetic energy after the collision. So my 2 colliding particles can come in. The total kinetic energy going in has to come out. That doesn't mean that it's the same for each particle. It just means that the total is the same after as it was before. And then a couple of helpful things here. The velocity, or the kinetic energy, of the gas particles is proportional to the temperature of the sample. This is one where we've got to be a little bit careful. Is proportional to the temperature of the sample. But remember, when we were talking about temperature units, we differentiated between arbitrary and absolute units. When we're talking about energy and temperature, we better use an absolute unit, because when we're talking about energy, we might want to talk about something having 0 energy. Well, we better not say it has negative energy, because that just doesn't really make sense. So we need an absolute temperature scale to use, and you're going to see all through here we're going to be using Kelvin temperatures on pretty much everything, so that we've got that absolute scale and not just one that's been arbitrarily set by the properties of water. And finally, as I said the last slide, attractive and repulsive intermolecular forces are negligible. They're not gone, they haven't disappeared. They're just negligible because of both the kinetic energy, the speed of the particles, and the space between them. So this is a theory, and a theory is, if we're thinking in scientific hierarchy terms, a theory is a model or a group of explanations of why things happen. When you see a theory, when you see someone talking about a theory, theories should be explaining why things happen, not necessarily what's happening. It's not just a description, it's an explanation of why things happen. One of the other really handy things about gases is they've got a property that solids and liquids, well, solids and liquids have pressure, but it's really not too variable. You can't really compress a liquid or a solid that much in most cases. But in a gas, because we've got large spaces between tiny particles, we can compress or expand those as much as we want. One thing to remember, just thinking about pressure, when we're talking about pressure in a gas, when we're talking about a gas pressure, what we're talking about is collisions with the walls. That's what gives us pressure. So pressure isn't some magic mystical thing. Pressure is wall of the container, gas particle colliding with it to give us that pressure. We've got a lot of pressure units. Gases have been very, very, very extensively studied for a long time because they're pretty well behaved. So pressure units that we're going to be using, first of all, the SI pressure unit is the Pascal. A Pascal is 1 Newton, which is a force, per meter squared, which is an area. So we can think about that as a pressure, right? Force per area. Because we've got a lot of different places and different ways we use pressure, there are a bunch of other ones in here, just ones that you're most likely to run into. So there's a pressure unit called a bar. 1 bar is 10 to the 5th pascals, or it's 100 kilopascals. So bar and pascal are just sort of directly related by a scaling factor. A bar is called a bar because, well, it's the same reason we measure pressure, atmospheric pressure at least, with a barometer, right? So barometer and a bar pressure unit. We also have one called an atmosphere. So we've got a standard atmosphere that was originally defined as the atmospheric pressure at sea level at a certain humidity. So there were a lot of conditions, but it was an actual measured quantity. Now it's a defined quantity. Atmosphere is related to bar by this relationship. So 1 bar is 1.01325 atmosphere. So you see that a bar and an atmosphere are actually really close to each other as far as units go. Then we get into some more sort of historical ones, and these are largely related to atmospheres. Millimeters of mercury. So old barometers were made with mercury. So we actually literally measured how long a column of mercury was that was suspended inside of a barometer. So millimeters of mercury, 1 atmosphere is 760 millimeters of mercury. So there's that relationship. And then just to make it more fun, millimeters of mercury can be kind of an awkward unit to use. So there's this unit called the torr. So 1 torr is 1 millimeter of mercury. So they're the exact same unit. It's just what we call them. 760 torr is 1 atmosphere. Torr, named after Italian. What was his name? It was Torricelli, but I forget his first name off the top of my head. And then the one that we're maybe most used to using in normal everyday life is pounds per square inch. We use that for lots of inflation measurements, whether it's tires or basketballs or any of those kind of things. Pounds per square inch, again, just like a Newton per square meter, pounds, force unit, per square inch, area unit. So 1 psi, just to relate these together, 1 psi is almost 7,000 pascals. So you see, a pascal is a pretty small unit. And 1 psi is also somewhere just shy of 52 torr, if you're using that bunch of units. So let's take a look at a conversion. Your car tires are supposed to be inflated to 35.00 psi. Now, they don't expect you to have 4 sig figs here, but in this problem, I gave it 4 sig figs just to keep us on track. So 35.00 psi, you have your tire pressure checked at SID's SI Service Center, where they only use SI units. And SID tells you that your left front tire is at 176,948 pascals of pressure. Should SID add air, remove air, or is the pressure just fine in that tire? So let's convert this pascals over to psi. Grabbed a number from the previous slide. So 176,948 pascals times 1 psi per 6894.76 pascals. My left front tire was at 25.6641 psi. That's a little on the low side, and we really should add some air to that. And safety note here, improperly inflated tires are actually dangerous. In addition to just being expensive and causing bad gas mileage or faster tire wear, they can be dangerous. So if you own a vehicle, you should check those tire pressures regularly. It's a lot easier to do when it's not the middle of winter, but you should still go out of your way to make sure that you're checking those tire pressures and staying safe. We're going to be working with pressures a whole lot. You'll have lots of opportunities to do some conversions. So it's just like any other conversion factor. Just figure out the relationship and multiply by that fancy version of 1. See you next time.